So what I'm going to do today is tell you a little bit about the FASTMath project. This is a project that has been part of the SIDAC program. So SIDAC is a large DOE program for scientific discovery through advanced computing. It's been around now for about 13 years, and the real focus of the SIDAC program is to bring advanced mathematics, computer science together with application scientists to help make sure their applications can be solved as efficiently as possible on the current generation of machines. Now, the FASTMath project is the applied math project within this version of the SIDAC program. It's a large project, about 45 named investigators, so it is a large team. And we're focused on a wide variety of applied math algorithms. But where I wanted to get started was because, like last year, this year, there are some folks who don't have a lot of background in applied math. And so for those who do have deep expertise in applied math, you can maybe tune me out for the next 3 minutes, because I'm going to talk about where that tri-diagonal system that everybody's been talking about, I'm going to show you where that comes from. Just to give you some context for everything that's going to come today and tomorrow morning. So when we're solving very large-scale applications on computers, there are a lot of steps that we need to go through in order to make that happen. And so the very first thing that needs to happen is that you need to develop a mathematical model to address the physical phenomenon that you're interested in solving. So everything that's around us, the weather, electrical currents through cell phones, all those things can be modeled using mathematical equations, PDEs, ODEs, et cetera. So you need to develop, that model, what you're going to include, what you're going to not include, and then create a discretization of that. So often these physical phenomena are going to be in complex geometry. So if you look at the figure right there in the upper right, very complex domains. Most of the times you can't find analytic solutions to the PDEs on those complicated domains, and so you need to do something about breaking it up into simpler problems. And that's called discretization. And so there are lots of ways to discretize a problem, and essentially what you're doing is you're taking the domain and you're breaking it up into small pieces, either little squares, triangles, hexahedra, tetrahedra. Trying to do that in ways that are automatic can be very challenging, and that's part of what the FASTMath team is addressing. But you also want to discretize the equations. So once you have the little pieces of geometry that you're going to solve it on, you can represent the equations in lots of different ways as well. Finite difference techniques, finite volume techniques, finite element techniques are all different ways of getting a discrete representation of those mathematical models on the discrete domain. From that, you'll generate an algebraic system, either linear or nonlinear. These are often quite large and need to be solved. And potentially, you'll solve the application on your parallel computer and maybe decide that you have too much error in one part of the domain or not enough resolution. And so you might want to refine your grid, your mesh, your model, and iterate that process. So these steps can require a lot of very sophisticated software. Ranging from CAD models to automatic grid generation for both structured and unstructured grids, high-order discretization, time integration techniques, lots of different ways to solve algebraic systems, which Jim and David talked about a bit, eigensolvers, mesh refinement strategies, coupling methods, and the list goes on and on and on. So it's a very complex process. But again, just to give you a context, we'll start with the simplest thing that you'll learn if you're a math student in your junior, senior levels of undergrad, where consider yourself having a one-dimensional rod. One end of that is in a hot water bath, the other end is in a cold water bath. Intuitively, you know what's going to happen in the steady state, right? This end of the rod is going to be very, very hot, and it's going to be sort of a linear progression down to the cold water temperature. And so you know that there's a diffusion process that's happening there. That will equilibrate the temperature in that rod over time. Well, that's represented mathematically using a Laplacian operator. So the temperature is going to be over time. You have your hot water bath initial condition at 180 degrees, for example, your cold water bath at 0 degrees. So to discretize that, again, very simple technique using finite difference methods. You'll place discrete points along that rod. Perhaps they're equally spaced with grid spacing h. And one of the things that you can think about is, well, I know that the temperature at any given point on my rod is going to be the average of the temperature on the points around it. And so you represent that discretely with this kind of an equation for the Laplacian. And then you have, a T0, your initial point is 180 degrees, and at T sub n, the last point in your domain, has got a boundary condition of 0 degrees. And so you can see that the coefficients for the different T sub I, you've got 1, a -2, and a 1. So if you want to solve the problem for all the T sub I in the domain, you would go ahead and set that up as a linear system. And this is a tridiagonal system where you can see, I've got my 2 -1s, coefficients for my unknown temperatures, T sub 1 through T sub n -1, and then my boundary conditions on the right-hand side. Right? So this gives you a linear system that you'll need to solve, and that you then visualize and analyze the results and maybe, again, refine. So that's the basic context for the numerical methods that we're going to be talking about. As the problems get more and more complicated, so do all the steps in the process. And so where the challenges start to come in is when you want to start doing things for very sophisticated physical phenomenon, very complicated physical phenomenon, complicated domains, very, very large systems. So you can use different kinds of discretization strategies for different needs. So if you have simpler domains or a need for a lot of efficiency, you might consider using structured grids or block structured grids. Those have very nice properties in that you can represent them very efficiently using arrays. So IJK access, it's very fast, it's very memory efficient. But they tend to have complications. For example, when you're doing adaptive mesh refinement, you can see there's a coarse grid and there might be a fine grid embedded within that. And so doing the discretization at those coarse-fine interfaces can be challenging. And in fact, there's still a lot of research that's being done when we're introducing these methods into new physical problems. How do you get that right? How do you maintain the accuracy, the high order? How do you maintain stability at those interfaces? In contrast, you can use unstructured grids, which would be triangles or quadrilateral. They're very flexible in that you can represent complicated domains pretty easily. The grid generation process tends to be a little bit more automatic, particularly for tetrahedral type meshes. But those have the challenge in that because they're not structured, the data structures that you need to represent the grids are much more complicated in general. And so they're not as memory efficient. The algorithms that you operate that you use to operate on those types of grids can be more complicated. And so there are trade-offs between the two different basic kinds of grids. So most problems are not as simple as the 1D, heat equation on a rod. Most of the time, it's very time dependent. Most of the physical phenomena we're interested in are nonlinear. And so that introduces additional kinds of solvers. So not just linear algebraic solvers, but also nonlinear solvers and methodologies. We're all moving increasingly toward multi-scale, multi-physics, multi-model. So combining those different physical processes together can be very challenging from the perspective of, what kinds of stability constraints do you have when you start coupling different physical phenomena together? And those interactions require a lot of careful thinking from an algorithmic and mathematical perspective. And then finally, increasingly, we want predictability in our simulations, or we want to be able to do things like choose a good design or automate the design process. And so that involves a lot of additional algorithms, for example, in uncertainty quantification. So we understand exactly how much error we have in our simulations, or optimization-based techniques so that we can go through a set of different design parameters and more automatically choose them rather than relying on the physicists or engineers' intuition and expertise. So as the problem sizes grow, the linear systems that I showed, nonlinear systems, also grow. So we are now at the point where we are targeting, linear systems with billions of unknowns. The systems are extremely large, And having the software to solve those systems is increasingly complex. So there's lots of different solver methods, like direct methods, iterative techniques. Simple examples are Gaussian elimination and Krylov type methods. Typically, preconditioning is going to be absolutely critical. In the case of iterative techniques, a lot of people are looking at physics-based preconditioning. What are the preconditioning strategies that we can use that are really well aligned with the physics that are going on, right? That make it more efficient. In addition, there are links between the mesh that I showed you on the previous slide, unstructured grids, and the linear system solution. So it turns out the quality of that mesh can dramatically impact the convergence rates that you'll see on your linear system solution. So there's lots of interactions between the different parts of the solution process. And there are lots of software tools that have been developed by the Department of Energy that deliver this kind of functionality. Basically, this just kind of wraps all of that up in a bow. Exascale computing is a really exciting time because there's lots of opportunity for higher fidelity simulations, more accurate simulations, much more sophisticated things that we're going to be able to do with a computer. But that's driving much more complicated software processes and packages. And so what I showed you earlier had just a few of these middle bars as the basic building blocks, but you also have to worry a lot about getting the data in and out of the machine, and adaptive solution techniques, steering, visualization, collaboration across lots of different institutions, and optimization, computing derivatives. All of that is very, very, it's a very complex ecosystem that we're striving to support. And it's made even more complicated by the fact that computers are changing. As the number of cores increases, we increasingly have to worry about different kinds of challenges. And we are getting to the point where power is becoming a first-class concern in terms of how we think about our algorithms and how we think about how we design our software. So right now, I would say, when you even think about things like debugging on a couple of thousand cores, standard technologies break down, and you have to do different sorts of things. And so, for example, using increasingly statistical-based type methodologies to help identify, all right, well, which core could this be going on wrong on, since you can't look at all million cores. So worried a lot about load balance. This is getting, again, increasingly challenging because of the deeper memory hierarchies. Fault tolerance. There's a lot of controversy and debate, I think, in the community about how important it is for the algorithmic side of the house to be worried about fault tolerance versus will it be taken care of by the machine. We all know that there's going to be a lot more failures as we go forward, but we don't yet know what the implications are for our algorithms. So lots of interesting discussions are happening in the community right now around all of these different issues. And so the challenges facing the application scientists then stem from all of this complexity. Complexity in the software base, the library base, the increased physics that they can do, the performance that they want to get on the machines, which are increasingly complicated. And so what it's leading to in general is that application lifecycle costs are increasing rather dramatically. And so it's taking longer and longer to build applications for these machines, to debug them, to get them to perform well. And particularly if you want them to perform well on all the different kinds of architectures that are being made available today. And so increasingly there's too much energy focused on too many details. And I think a lot of the application scientists, have been indicating for a long time, I'm not getting the time I want to do my physics, to do my science. And so that's what the FASTMath Institute is trying to help address. So our goal in the FASTMath Institute is to deploy the scalable mathematical libraries that the application scientists need to help them do their jobs better. And so we're particularly interested in the simulation of very complex phenomena. And we're interested in doing it on the machines that are available today and getting ready for the machines that are going to be available in 3 to 5 years. And so that's really where FASTMath, the sweet spot is. In general, we encompass 3 broad topical areas. So the first is tools for problem discretization. So this is the structured grids and the unstructured grid technologies. In particular, we're very focused on high-order methods. Trending up is high-order methods. Trending down is first-order type methods or even second-order type methods. So we're very interested in how you do high-order methods. Complex geometry, particle methods, which are widely used in DOE applications, and then time discretization and time integration type techniques. And then the solution of algebraic systems. So these are the very large-scale linear and nonlinear systems. In our center, we have expertise with both linear and nonlinear, both iterative and direct solvers, as well as linear and nonlinear systems, and eigensystems. We had some work in differential variational inequalities, although that's been not a key focus area for us in the last year or so. And then finally, because FASTMath is such a large center and it brings together those first 2 columns, we had a really nice and unique opportunity to focus on what can we do to produce more high-level integrated capabilities. And so, for example, when you have very sophisticated meshing infrastructures talking to very sophisticated solver infrastructures, sometimes there are inefficiencies that are introduced in that process. So Jim mentioned, just 2 kernels talking to each other being somewhat inefficient. Well, you can imagine that might also be true if you've got, for example, Chombo talking to PETC as 2 very large-scale packages. How do you marshal the resources, the data, particularly on the deep memory hierarchies that we have today? So we've been looking a lot at mesh solver type interactions, particularly in the context of adaptive mesh refinement, coupling different meshes together, coupling different physics domains together, management of field data. So there are lots of different things that we're doing as a center that we are not able to do individually. So what I'd like to do for the next couple of minutes is talk just at a very high level about some of the capabilities that we're developing in the center. The first is the structured grid capabilities, where the focus, as I mentioned, is really very much on high-order methods and particle techniques and complex geometry. So in the first column, we're thinking about block structured AMR. So these are techniques that have been around since the 80s, and they've been widely used in a lot of different application domains. But as I mentioned earlier, there are key pieces of research that need to be done, for example, on coarse fine boundaries to maintain accuracy and across those boundaries. When you start thinking about complex geometries, so things that you can't represent with just a single grid or that have highly anisotropic regions within them, you might start to think about map multigrid type methods. So this is where you would map a grid to part of the domain, chop up the domain, have another mapped grid map to that other part of the domain. They'll abut, right? And you'll assume that the solution is continuous across that interface, but you might have discontinuous derivatives in that case. And some of the challenges there, again, are how do you maintain accuracy? You typically lose an order of accuracy at that interface. And so one of the things that we're researching is what can we do to introduce, fourth-order methods in these map multi-block type techniques for different kinds of physics problems so that we can maintain second-order accuracy overall, right? So there's some of the research challenges there. Embedded boundary methods. So this is probably the easiest grid generation technique out there. So you have a very complex domain, you plop down your Cartesian grid on top of it, and you cut out the cells. And ta-da, you're done with your grid generation. So you can do very complicated domains very quickly. Challenge, at that boundary of the domain, you end up with some very odd-looking cells, some of them which can be quite small. And that, in turn, can impact, for example, CFL numbers, these constraints on time stepping, how big your time step can be in a numerical method. And so there's research on how to deal with those boundaries and doing it in different applications. And then particle-based methods. Like I said, in the Department of Energy, particle-based methods are used for a lot of different applications. So in cosmology, there are particles that are being used with phase space distributions So charged particles you have in fusion applications or accelerator type applications. And so there are lots of interesting questions that get introduced here, for example, about load balancing. So if you've got a particle simulation that's embedded in a continuous simulation, right? So you've got continuum PDEs interacting with particles. How do you do the load balancing on that in ways that are going to represent well both aspects of the simulation? Because you might want different decomposition for the continuous space than you have for the particles. So how do you deal with that? This is a case, again, I think in your trending up slide you had variable precision as something that is trending up. This is a case where oftentimes single precision is good enough. And so how do you weigh the trade-offs between single precision and double precision when you're evaluating these kinds of algorithms? In the unstructured grid side, it's very similar. Let me just say quickly that there are two primary code bases that we are using on the structured grid side. One is Chombo, developed by Phil Kalel and his team at Lawrence Berkeley National Lab, and the other is BoxLib, developed by John Bell and Ann Algrim at Lawrence Berkeley National Lab. On the unstructured grid side, we also have two software infrastructure code bases that we use. One is PUMI, which is Parallel Unstructured Mesh Interface, developed by Mark Shepard and team at Rensselaer Polytechnic. And the other is MOAB, Mesh-Oriented Application Database, I think. So they both do the same high-level thing, but they are, again, targeting slightly different domains. So PUMI is primarily focused on how do you do adaptive mesh refinement at very, very massive scale. And so doing that refinement, getting the physics involved there is critical. Then on MOAB, that's more focused on can you do representations of unstructured grids or mixes of structured and unstructured grids in very memory efficient ways using array-based data structures. So they have different areas where they're going to perform very well. And so getting those to scale well on hundreds of thousands of cores is something that we've been focusing on. And of course, when you're doing adaptive mesh refinement, dynamic load balancing is absolutely critical. And we have a number of different techniques that we're exploring, ranging from geometric techniques that can be done very efficiently and very quickly, in line, in situ, in the simulation, but also starting to look at things like if you have a very deep memory hierarchy where you've got many cores on a node, and then you also have off-node partitioning that you need to do. Are two-level techniques going to be better than single-level techniques? So two-level partitioning techniques. And the answer, as it turns out, is yes. So we've been exploring those kinds of hierarchical partitioning methods, and we've shown that you get, for example, a 30% faster runtime overall when you take those deeper memory hierarchies explicitly into account in the partitioning strategies. For mesh adaptation and quality control, we're primarily, again, interested in high-order meshes. So for unstructured grid, you can start to imagine your triangles now have curved sides, or your quadrilaterals have curved sides. And so there are lots of interesting issues that come up there in terms of, how do you control the quality of those kinds of elements? What does that look like? How do you do that for very highly anisotropic domains? How do you make sure that they're not invalid elements? So those are the kinds of things that we're looking at from an algorithmic perspective. And then, of course, parallel performance, scaling things to very, very large numbers of processing cores are something that are front and center in our center. For algebraic systems, this is probably the largest part of the FASTMath Center. We spend probably about half of our resources on the solution of algebraic systems because they are such an important part of almost every application that's out there. So again, we focus on linear, nonlinear, and eigensystem type systems for the most part. For linear system solution, as I mentioned earlier, we're doing a lot of work with what do we need to do to make sure that iterative solution techniques or algebraic multigrid techniques are going to be efficient on next generation computers. So a lot of our work in the linear system solution is really focused on next gen architectures and what that needs to look like. For nonlinear systems, there's lots of interesting research problems here where we're increasingly encountering problems that may have discontinuities in the solution process. And so how do you solve nonlinear systems where you may have unknowns appearing out of nowhere, right, in dislocation dynamics type applications? Or homotopy type methods where you use a globalized technique to have a sort of a warm start. You start with an easier problem and you solve that and use that easier problem's solution as a starting point for a slightly harder problem that's closer to the real problem you want to solve. And you do that iteratively until you get to the problem you actually want to solve, but now you're close enough with the Newton's method's starting point that you can solve that problem successfully. For eigensolvers, there's a lot of work we're doing both for iterative techniques and optimization-based techniques. The eigensystems are coming up in a lot of different applications, and they're for both symmetric and non-symmetric systems, nonlinear systems. And so there's a lot of individual techniques that we're exploring in terms of how do we create new methods that have more concurrency in them than maybe previous solution techniques did. And then finally, the integrated technologies, I already mentioned a lot of these, so I won't spend too much time on them. So you have the mesh solver interaction methods, mesh to solver coupling methods, and then the unstructured mesh technologies into a simulation workflow. So there have been lots of tools that have been developed to deal with unstructured grids. How do you get them to all work together efficiently to solve an application problem? So as I mentioned, a lot of our algorithm development is encapsulated in software that's widely used. So this is just the list of the FASTMath software and the various areas where it's applied. So structured grid tools, unstructured mesh tools, and partitioning tools, the eigensolvers, time integrators, linear and nonlinear solvers. So I'm not going to leave this up here much other than to say when you look at the presentation, there's a website on the last slide, and there's a software catalog from that website where you can find out more information about all of these different software packages. So I've been mentioning all along that a good chunk of our research is aimed at improving performance on next generation systems, and it's focused both on what we need to do within a node. So the intranode, the deep memory hierarchies, and also across nodes, so internode. And so we have research efforts that are focused on things like reducing communication. How do we create algorithms that have much more concurrency in them? So trading off communication for doing extra computation, or trading off more computation to get an overall faster time to solution. Reducing synchronization points, and so again, things like pipeline GMRes, where you want to reduce the number of synchronization points. You can find that just by reducing those all-to-all type messages in GMRes type methods, you can increase the overall performance of the method by 20% by reducing that communication cost by as much as half. One of the interesting things that we have found using mixed programming model, so that's MPI plus something, in our case it's typically OpenMP, is that that'll often reduce the memory footprint. So it may or may not give some of our algorithms an increase in performance compared to an all MPI code, but almost always it will reduce the memory footprint, sometimes by a factor of 5 or more. And so that's been an interesting side effect of moving to the hybrid programming model. So the new algorithms that are addressing some of the key bottlenecks on modern day computers, it's these kinds of algorithms that we've needed to develop that are allowing our software and our mathematics to scale. So for example, in the area of reducing communication, you heard from Jim Demel, but in algebraic multigrid, for example, there are these Galerkin approaches which are based on a three-way matrix multiplication, so 3 matrices multiplied together. And there are lots of different ways that you can reduce communication in that instance. So for example, you can just leave out some of the entries in the multiplied matrix. and evaluate how does that impact your convergence, when you leave out those entries. You can do an additive type technique instead of a multiplicative type technique, which tends to be faster in performance, but converge not quite as fast. And so what are the trade-offs that you see when you do that? When you do hierarchical partitioning, I already mentioned that you can optimize communication at each level in the hierarchy, both inter and intra node, and achieve an overall speed of about 30% on matrix vector multiplies just by taking that into account. Increasing concurrency, there are a number of different things that we're looking at. For example, in eigensystem solvers, we are looking at developing new algorithms that have increased concurrency and allow you to solve for tens of thousands of eigenvalues, eigenpairs concurrently, whereas before you couldn't do that using things like spectrum slicing type methods. A nice result is that we've been using the blue gene architecture, which is a very massive. I think you guys have access to Mirror or Vesta. Is that a blue gene? I don't remember. So there are a number of blue genes floating around the world that have massive scale, and Mark Shepard and his team have looking at extreme scaling demonstrations for unstructured grid simulations, where they've looked at 3.1 million processes on 3/4 of a million cores, and again 92 billion node points for that. So just a massive computation, and then trying to understand how does that scale when you get to that size of a system. Reducing the synchronization points, I already mentioned the pipeline GMRes and Krylov methods. Memory footprint issues, so predictive load balancing is another key way. So if you can anticipate where you're going to do adaptive mesh refinement and actually migrate nodes to those processors before you do the mesh refinement rather than after. In some cases, that was actually causing the simulation to fail because it was running out of memory. And so you want to be able to predict these things and migrate early. And then increasing the communication and computation overlap. So in SuperLU, one of our direct system solves, if you can improve the look-ahead algorithms, you can get a runtime improvement of about 3x just by, again, hiding those communication costs that we've been talking about all morning. So there are a number of different application areas that we have been able to impact with these solution techniques. So I just want to give a few examples. The first is accelerator modeling. So this is the SLAC system where you have an unstructured grid, and they've been using sparse direct solves in PDS-Lin, which is one of our software packages, to improve the time to solution that they are able to achieve by about a factor of 20. And they've also been able to reduce the memory footprint by about a factor of 5 using some of the solvers that we have rather than the native solvers that they were using. And this has allowed them for the first time to do an 8-cavity simulation that they weren't previously able to do. And so by reducing time to solution, that allows them to run bigger problems. In the area of mesh generation, we've been working with scientists in the fusion community who are modeling these advanced tokamak systems, which have some very challenging mesh generation issues that were causing them to spend hours generating a mesh for each one of their simulations. So using some of our automated tools, we reduced the mesh generation time from about 11.5 hours down to a minute, right? So again, automating some of what was being difficult. This significantly increases the efficiency of their workflows, right? So those are a couple of examples where reducing time to solution has happened, but we've also been focused on increasing accuracy as well and fidelity. So for example, if you look at ice sheet modeling in Antarctica and Greenland, if you can use adaptive mesh refinement to follow the grounding lines between the ice and the water, you can actually get much higher resolution, which means that you get a more accurate simulation. And for the first time, they matched experiment for ice sheet modeling that they hadn't been able to do previously. In cosmology, they're looking at dark energy and looking at clustering algorithms for dark energy. And again, using adaptive mesh refinement, this time structured adaptive mesh refinement well, both are structured adaptive mesh refinement. They were able to simulate a much larger resolution simulation. So they were able to get 4096 cubed in an 80 megaparsec box to produce statistics on dark energy and clustering at a 1% level of accuracy, which is, again, something that's really needed for some of the missions associated with dark energy, BOSS and Big BOSS. And then finally, one of the things that we've been trying to do as well as a team is lower the barriers to adopting our software. So a lot of people want to use, Chombo together with PETSI, together with Hyper, together with sundials, right? Do a big tool chain. And if you've ever tried to do that, you know that that can be painful, right? Very painful. So there are lots of different build and configuration management type practices. There can be namespace collisions. There can be different ways of potentially spoofing MPI or referencing MPI, different access of, versions of external libraries that multiple packages need. So that can be a real challenge. So one of the things that we've been trying to do, and to be quite frank, one of our motivations for coming and talking to you, other than we want to introduce you to our software, is it's provided a great focal point for us to try to get our software working together on Vesta, right? For example, and looking at and addressing some of these issues. So I mentioned that this is a large team. Our goals for this tutorial are to provide a basic understanding of the applied math software that are being developed as part of our center, particularly focusing on linear, nonlinear, ODE solvers, as well as the discretization technologies that I've been talking about. We would like to provide an overview of many of the FASTMath software tools that are available to perform these tasks, and then give you an opportunity to practice using them in our hands-on sessions. And with that, I will conclude. So this is how you can get a hold of us in the different areas. This is information that's available on our website.